In this video, we will look at an ad hoc problem that recently appeared in a Codeforces round. And of course, whenever these kind of ad hoc problems appears in Codeforces round, there is a lot of controversy behind it. But I still believe that this is a nice problem to solve because you either know the trick behind this kind of problems and you are able to solve it instantly. Otherwise, you can keep on trying various greedy strategies, none of them might work. So in case you are not aware of how to solve these kind of problems, I hope that this video can serve as the catalyst for you to know that these are the tricks that you have to use for these kind of problems. So let's start with the problem description. It says that you are given an array containing of some positive integers, and in one operation you can select any element. Suppose the element that you have selected is x. Then if this element is odd, you increment it by 1, or if it is even, you divide it by 2. This constitutes as one operation. And of course, in the next operation, you can select any other element. You can also select this element multiple times. So the problem statement is for you to find out what is the minimum number of moves that you need to make on this array such that all the elements become equal. How do you solve this problem? So even before solving this problem, even before trying to find out the minimum number of moves, let's try to see if there is if the answer always exists. That is, regardless of the number of moves, can you actually make all the elements equal, or is it not possible at all? So we can start with an example. Suppose the element that you have started with is 23. Since it is odd, you increment it by 1, it will become even, and then you divide it by 2 since it is even. So it becomes 12. 12 is also divisible by 2, divided by 2, it becomes 6. Then it becomes 3. 3 is odd, so you increment, then it becomes even, and then you divide it by 2, and then it goes to 1. So one thing that you can notice right out of the box is that every number will eventually reach 1. Why is this true? Why will it not get stuck in a loop, and why will it actually reach 1? Because you can see that if it is even, so let's consider this on a number line. If this is the number line and you are standing at this number over here, so you can notice that if it is even, then this number will now land at x by 2. So you see that this number is coming closer towards 1, but we still have to prove that it will not get stuck in a loop. But you can see that if it is now odd, then it will just take one step to the right and then again go back to the left, then one step to the right and again go back, one step to the right and again go back, one step to the right and then again go back. So every number will eventually reach 1, that is for sure. And then if it comes to the worst case, you can always set all the elements to 1, and that is one possible strategy to make all the elements equal. Might not be optimal, that's fine, but we know that a solution does exist. Now, how do you find out the minimum number of moves? Because there could be multiple strategies to make all the elements equal to z, but how do you know that this is z is the minimal final value that you should try? So in these kind of problems, even before solving it on an entire array, what I like to do is focus on just two elements at the start. That is, suppose if you have an element x and you want to know whether you can actually reach y from that element or not. That is, instead of considering it as y, let's call it as target. You want to know, can you reach this target value from this value x? Can you quickly answer this question? Because if we can find out what are the possible target values that we can reach, then maybe we can have some brute force solution where we try out all the possible target values for each exercise. Time complexity might be bad, that's fine, but at least we will have a correct solution which finds the minimum number of moves. So for each element x, we want to find out what are the possible targets that we could reach. But even before doing that, we want to know that given this element x, can you reach this target? How do you solve this? So let's again look at it from the number line, and suppose this target is over here. This is your target. Now if x is here, then you can see that since there is a very big gap between x and target, and you know that there is only one way for x to proceed, that is the path is already predetermined. If it is odd, you have to increment by 1, and if it is even, you have to divide it by 2. So since target is fixed over here, then if x is even, it will come over here, it will be divisible by 2, so you divide it by 2. Otherwise, if it becomes odd, then you go one step forward and then you come back like so. So this means that if you want to find out whether you can reach, like you can define it recursively, that is if you want to find out whether this whether this x can reach the target. So if you define this function x comma target, and the function definition says that this function returns yes if x can actually reach the target, otherwise it returns no. Then you can see that all you have to do in this function, you can simulate it by saying that if x is over here, if x is to the left hand side, if is to the left hand side, then you can see that x cannot reach target in all the cases except once. What is that case? Because you know that the optimal path looks something like this. You either go back, or you go one step forward and then you go back. So if you have a big gap between you and the target, if you have this gap, then of course you cannot reach the target. So if x is less than target, then the only possible way, because all of these operations, they only take you backwards, they can take you forward just one step at best. Like if this is odd, then it could be this case, but otherwise they take you big jumps to the backward. So this means that you can say something like, let's define next of x, and next of x we define as x plus 1 if x is odd, and you this would be x by 2 if x is even. This is by definition. So we just define a helper function that can quickly determine what is the next node on your journey that you started from x. Then you can see that if x is less than target, then the only possible way that x can reach target is that next of x should be equal to target, right? So if this is your target, if the target is 5, then the only smaller element that can reach 5 is actually nothing, because 4 cannot reach 5, and of course if you go one step uh, towards, more than one step towards the left, nobody can reach 5. But then if you have something like this, if this is 6, then you can see that 5 can actually reach 6, and nothing to the left of 5 can reach 6. And what about the elements to the right of 6? Then you can just apply a recursive strategy. That is, if they are very far, so you take the next step, be it going one step right or coming uh, back by a factor of 2. You keep on doing that until you eventually hit target. So with this, you will be able to quickly figure out whether an element x can reach a particular value t or not. Now let's talk about the time complexity, and I believe this is the part that is the most crucial. Now, if you start with the largest number, let's say if you start with the largest number that is given to you, which is 10 to the power 9, how many steps will it take to reach the target? Or regardless of what the target is, like what are the maximum number of steps that it will take, because we saw that every number eventually reaches 1. then you can see that you have this big number line. This is 1 and this is 10 to the power 9. You can see that if this number is even, you are immediately breaking the number line into two halves. This is the left half and this is the right half, and you are discarding the right half because now you are at this location. But if x is odd, then you might think that you are actually not discarding the number line, but actually that is not true, because if x is odd, then you are doing a little bit of extra work. And the extra work is that if x is odd, then you go just one step and then immediately you discard one half of the number line. So this means that at every two steps, so if you you can say that at every step x reduces by a factor of 2. At every two steps, at a maximum of two steps, x will reduce by a factor of 2. So this means that if the original number is 10 to the power 9, and you should know that 2 to the power 10 is roughly 10 to the power 3, if you are just talking about the order, because you know that 2 to the power 10 is 1024 and 10 to the power 3 is 1000. So this means 10 to the power 9 is what? 2 to the power 30, roughly, cubing both sides. This means that in just 60 steps, you will be able to reach 1. And this is the key idea that some of you might not know. That whenever a problem talks about dividing by 2, a major hint is that you will be able to reach 1 very quickly in either 30 steps or 60 steps. Actually, this 30 or 60 does not matter. What matters is the order of operations. What is the order? So the order would be log n. So if n is up to 10 to the power 9, when you're doing these journey, because the journey is fixed as per the problem, you don't have to actually make a choice, because the choice is predetermined whether you are odd or whether you are even. So on that basis, the choice is already predetermined. So this means that in just 60 steps, you will be able to reach 1. Now, this fact that we have just seen, this is actually more powerful than you think. In fact, this forms the basis of all the binary search algorithm that you might have seen. So we claim that sorting an array takes n log n, or doing a binary search takes a log n time. But how are we sure that binary search will exactly split it into equal halves? Because that is not guaranteed, right? Because the array length could itself be odd. The length of the array could be 2x plus 1. So in that case, one side would be smaller and one side would be bigger by 1. But even in this case, the time complexity of binary search is O of log n, because of exactly this thing. Like, if it is fine for an odd length array to exist, because when you cut it down, one part will be even and the other part would be odd, but in the next iteration it will eventually become even. So you are always dividing it by half, so it doesn't actually matter the total number of elements. What matters is that the order, which is O of log n. So now we know that in just 60 steps, at most 60 steps, you will reach 1. And this is quite manageable for us. But this tells us another thing. And what's that? Is that if you know that you will only take 60 steps to reach 1, and your journey is already predetermined, it means that all the numbers that you visit in your journey, they are also predetermined. This means that given one particular x, what are the possible targets that you can have? That is also predetermined. And what are these possible targets? These are nothing but the elements that you have encountered in your journey to 1. So now let us see how to use this info to solve the original problem. But before we look at the actual solution, let's go off track a bit and let's talk about this login, because we are here not just to solve this problem but also learn some reusable tricks that you can apply in future problems. Now, as we have already seen that if you repeatedly divide a number by 2, you know that after just 30 or 60 steps, or let's say that after log n steps, you will eventually reach 1. And this is something that even beginner level people can understand very easily. But it is funny how the human brain works, because you will see that the converse of this statement, that is, if you start with any number x and you keep on multiplying it by 2 every time, then how many steps before you reach a very big number? That is, if you start with 1, how many steps would you take to reach 10 to the power 9? Because this problem and this problem are basically the same, dividing by 2 repeatedly versus multiplying by 2 repeatedly. The number of steps should be log n. So if you think about it from that perspective, it's clear that repeated multiplication will also become greater than 10 to the power 9 in just log n steps. But most people find it very hard to believe this fact, and that is why you will see that all the algorithms and the data structures that use this repeated multiplication by 2 strategy, they are tagged as hard problems as compared to the ones that use the repeated division by 2 strategy. For example, if you look at this thing, if you look at the small to large trick on trees, so in the small to large merging tricks also you do the same thing. You have a set of size x and then you also have a set of size greater than or equal to x. So when you merge them, you get a set of size that is at least 2x, right? And then you can see that you are doing repeated multiplication by 2, and that is why you make that argument that since you are doing repeated multiplication by 2, in just log n steps the total number of elements in your set will become n, and that is why the time complexity of small to large merging is O of n log n, and people find it very hard to believe. Another very famous example is the case of LCM. So you will remember that I recently uploaded a video on my YouTube channel that talked about the congruency and LCM. And here also we had seen that same trick where we said that if you are taking LCM of two numbers, then if one is not the divisor of the other, then the LCM is at least double. It increases by a factor of at least 2. It means that in just log n steps your LCM will become very huge, and that was this observation itself was the crux due to which the problem was tagged as a hard problem. So there are actually a uh, lot of problems that I've seen in which repeated multiplication by 2, as soon as that factor comes in, the problem immediately becomes a hard problem. So that is something that was weird that I have observed that I wanted to share. But you should keep in mind that repeated division by 2 is equal to repeated multiplication by 2, and both of them have the same time complexity of O of log n. Now coming back to the original problem, how do we solve it? Now that we know that if you start with any number, no matter how big is it, like since the maximum number that you could start with is 10 to the power 9, it is actually possible to simulate it all the way down to 1. But we have to be careful with 1. Why do we have to be careful with 1? Because the algorithm doesn't tell you to terminate at 1, because 1 is odd, so you can actually go to 2, but 2 is even, so you can actually come back to 1. So actually there is a case where you could get stuck in a loop, but you can notice that what is the way to arrive at 1? The only way to arrive at 1 is by coming at this 2 first and then coming at this one. So this means that if you just apply this operation and then you apply a restriction by yourself saying that if you have reached 1, stop the algorithm, then you can be sure that in just 60 steps your algorithm will be terminated. So now that we know this fact, let's see how to solve the problem. So we have this array. Now another interesting fact that we have already seen before is that this operation that we have just described, it actually always decreases the number, because in some cases it increases it by just a small amount, which is that delta of 1, but then it immediately takes it back over here, then here, and then over here, then over here, and then over here. So since it is not possible to increase a number, what is one special element that you should be focusing on? This special element is the minimum element of this array, and this is one trick that is used quite a lot in these ad hoc problems. So that's why I wanted to create a video around it. So you should keep in mind that for some of these problems, focusing on the minima or the maxima might help you simplify things. Now you can notice that the minima has a unique path that will reach 1. So, and that path contains of at most 60 steps, because since if this is the minima, you take this minima and then you apply your strategy. It can reach here, it can reach here, it will reach here, and then finally in 60 steps, in at most 60 steps, it will eventually reach 1. Now you know that since all the numbers in this array have to be equal, then and minima also has to be equal to all of the numbers that you will be making them equal to. But you know that the path for the minima is already predetermined, and it contains a maximum of 60 elements. So we don't know what is the optimal path at which minima should stop, but one thing you do know, that the answer has to be one out of these 60 elements. So what you can do is you simply iterate minima, you simply apply the algorithm on the minima, you compute all the list of 60 elements that minima crosses through, and each of them is your possible candidate. So you have 60 possible candidates. Now once you have 60 possible candidates, you can try each of them. So suppose you have fixed a candidate z. Now you want to make all the elements equal to z using the minimum number of moves. But how do you do that? It's actually very simple, because if this is x and if this is z, then there is no strategy involved in minimizing the number of moves to achieve z, because we have already talked about the reachability problem here, right? This is the first thing that we have discussed, that if you want to check if x is reachable till target, then this is how you can do that. But to find out the minimum number of moves, there is no real strategy involved. Why is there no strategy involved? Because the path for x is already fixed. So the path for x is already fixed. So first of all, using this function, you can figure out whether both of them will be reachable or not. If it is not reachable, then you simply discard this z. But if it is reachable, then you know that the path of this x is already predetermined. So you keep on simulating this path, and of course you can afford to simulate it because it is just 60 steps, it is just log n steps. So you simulate it, and at this simulation, if you encounter z, then that has to be your minimum element, minimum number of operations, because there is no strategy to be applied and there is just one way to reach z. So this, in this manner, you can try out all the possible z. There could be log n such z, and how to compute these z. These z will exactly be the paths that the minima takes to reach 1, and you you pick each of these 60 elements as your possible final candidate, and then you try to make all the array elements equal to z. So now you can see that we have essentially applied a brute force algorithm, although in a smart way. We don't actually have to try out all the elements from 1 to 10 to the power 9 as the final candidates, because we know that these candidates can only be on the path in the that the minima takes, and this is the most crucial observation that is needed to solve this problem. Now let us talk about the time complexity of this algorithm. So what is the time complexity? So the first thing that we have done is compute the minima, that is of course O of n. Now this minima, how many candidates can it process till it reaches 1? The total number of candidates that it will process, we know that it is log n, because this minima itself could be 10 to the power 9. Now there are log n candidates, but once you fix a candidate z, how do you find out the minimum number of moves to reach z from this x, you can just simulate it. Why? Because we said that simulation only takes log n steps. So this means that you simulate here, 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 and here. So you can do the simulation for one candidate in n log n time, and there are log n candidates. So you have solved the problem in n log square n time complexity, which is acceptable. So now let us look at the implementation for this. So first of all, we write a simple utility function that will give us the next node in our chain, because our journey is already fixed. So if the number is odd, we increment it by 1. If it is even, we divide it by 2. And this function will actually help us to make sure that we don't spam these conditions everywhere. So that's why, since the journey is fixed, we have written a utility function to do this. We compute the next node. Now again, we have already discussed that you will pick the minima and you will trace the path that the minima takes to reach 1. But then whatever candidate that you pick, it is possible that not all the array elements will actually pass through this. So first of all, you figure out, can this x reach this target? And how do you do this? So you know that if the target is on the right hand side, and x is over here, then it's not possible, unless the situation is that you want to reach 1 from 2, or if it is not this case of 1 from 2, then it could be something like you want to reach 4 from 3. So that's why, to avoid the infinite loop, you can just check that if x is 1, because you can see that 1 can go to 2, but 2 can come back to 1. So this is just one small infinite loop that you would have to handle. So then if x is 1, then the only possible target that it can reach is either 1 or 2, that we know. Otherwise, we can consider 1 as an absorbing state. Then you can simply check if that the target has been reached, fine. Otherwise, you keep on making your journey until you reach target. Then this code will never get stuck in a infinite loop, and the time complexity is overflowing. Now once we know how to check if the target is reachable, we want to find out the minimum cost, and we said that there is no strategy. You just do the simulation, and this is your x. And since you know that the target is reachable, you don't actually have to add any corner case, if else, etc. Right? You just keep on doing the simulation and you will eventually reach this target. Right? So that's why this every time you take one step forward until you have reached the target, and using recursion you add up all these values. So why will this code not get stuck in an infinite loop? This is under the assumption that you use this function first before using this function which computes the minimum cost. And of course, the time complexity is again overflogging. And then for the minima, you want to find out how many nodes, unique nodes, that you encounter in your journey until you reach 1, right? So how many total unique nodes? They can be up till 60. And of course, a nice simulation that you do, since the total number of unique nodes is 60 and you do not repeat elements, then of course the time complexity will be O of log n. And since you don't want the process to continue once you have reached 1, because once it goes to 2 and then it can come back to 1 again, and then this can stuck in a loop. So that's why we say that 2 is always achievable. Why is 2 always achievable? Because 1 is always achievable, right? Anybody can land at 1, and then if they want, they can go back to 2. So these are the set of candidates, and then we tie it all together and solve the original problem, which was to find the minimum cost to make all the array elements equal. So you find out the minimum element, and then all the nodes that the minimum elements traverses through, they will be the possible candidates. So you iterate through all the candidates, and then you try to convert all the array elements to that candidate. But first you check if it is even possible. If it is not possible, then you set the cost to infinity. But if it is possible, you compute the minimum cost to convert that element to the target, and you sum it up across all the element, and that is your answer. So the time complexity now becomes n into log n into log n. So this log n is the list of candidates. This log n is for the simulation for each candidate, and this n comes from trying that simulation on each of the array element. So this is the n log n, n log square n solution. Now, if you have seen the video just this far, like you can still solve this problem and get an AC on this problem. And this is how most people already did in the contest, including me. But if you stop to think about it, you can actually solve this problem in O of n log n instead of O of n log n square, by noticing that the fact that is there anything special about the minima, like that minima argument that I've told you, that sure it is helpful in some of the problem, focusing on the minima might help you unlock things faster, but here it's not that helpful. Why? Because sure you are claiming that any number cannot increase much, so that's why the final candidate has to be one of the paths that the minima takes. But you can actually claim this same argument for any element of the array, even for the maxima. So even if x is the maxima, can you not claim that whatever the path the maxima is taking to reach 1, the final answer has to be one of these elements? And is there actually any benefit in picking the minima versus picking the maxima? So if you think about it, there is no benefit at all, because even maxima will terminate in 60 steps, even minima will terminate in 60 steps. So in fact, this code will also work if you delete this minimum element part and here you pick one random array element. This will still work in O of n log square n. So now that we have concluded that the minima is not special and this was not obvious to say, right? Can we conclude something more? Now, we are saying that for any random element, you do the simulation to make it reach 1, and then the list of candidates are the 60 elements that you encounter on your path. Can we trim down this list further? Turns out that you can actually do that by noticing the fact that suppose you just had two elements, x and y, right? If you just had these two elements, x and y, and you wanted to make both of these elements equal, but this time you can either change x or you can change y, then you can notice that previously we fixed one target over here and we decided that okay, is x reachable from target or not? There is a unique answer. And what is the minimum number of steps? There is also a unique answer. But now if you are allowed to change both x and y, and this time I tell you that the array is of length 2, now equalize them, then would you still have to try out 60 candidates, or can you trim down the list? Then if you plot them on a number line, if this is your x, if this is your y, suppose y is on the right hand side, then if you are trying to make them equal, then they will have a meeting point somewhere, that is along there. So each x and each y, they have a unique journey to 1, then their journey should intersect at this point. Now we want to find whether this intersection point is unique or there could be multiple intersection point. Then you can notice that if y is on the right hand side, then no need to, if you want to minimize the number of operation, you wait for y to come towards you. So y will be divided by 2 and y reaches over here. Then y will be divided by 2, y reaches over here. Then increments by 1 and then reaches over here. So as long as y is to the right hand side of you, you keep doing the operation on y until this situation arrives that y is equal to x plus 1 and x is odd, then you can go to y. So in this case you can see that the meeting point is unique. Otherwise, suppose y is not on the right hand side. If the y is not on the right hand side, it means that y is on the left hand side. If this is x, then this is y. But you can flip that same argument around and you can say that okay, x is on the right hand side, so you have to keep on decreasing x, right? You have to keep on decreasing x, and if x goes behind this y, then y is on the right hand side, and then you can you keep on decreasing this. So now you can see that actually there is a unique meeting point between x and y. There can't be multiple meeting points, because once they meet, why can't there be multiple meeting points? Because let's say, suppose this is their meeting point. At this point, x and y have become equal. This is one possibility for them to become equal. So once they have become equal, they'll follow that same journey, because the number is same, so the journey will also be the same. So now that we know that the meeting point is unique, if this is the meeting point, like if x is coming over here and then y is coming from here, so this is the unique meeting point. So if this is their unique meeting point, then first of all we can check if x is reachable from y or not, and we already know what is the minimum number of steps that are needed to reach y from x. So if the meeting point of two elements are fixed, then we don't actually have to try out all the 60 candidates. Therefore, you can conclude that the meeting point is for two elements is unique. So of course the meeting points for three elements will also be unique, because x and y meet at the common point m. Then x, y and z should also meet at some common point m. And in fact, you can extend this reasoning to the entire array, and then you can conclude that all of them will meet at a single point m, and this is actually uniquely determined. So you don't actually have to try all 60 possibility, you can try just one possibility. So this candidate list and this minima thing, this was just, if you think about it, this was just a diversion, because these minima observations are very helpful to solve this problem in other settings, but at least in this variation, minima or maxima doesn't matter. So this login itself is not needed, because two elements will have a unique meeting point. Now again, if you are still not convinced that, so for two elements we know that they will have a unique meeting point, but why does this argument hold for the entire array? What if introducing three elements may what if introducing three elements creates two different meeting points? So that will also not happen, because see, if there is a unique meeting point between x and y, then the chain will look like something like this. This is the chain for x, and then y has merged into this chain only at this point. This is the unique meeting point m. Now when the third element is introduced, we are not claiming that this meeting point will be the same, but what we are claiming that there can only be one meeting point for all of these three elements, because after this point you can think of it as so if z wants to merge into this chain, suppose z is merging over here, then it still doesn't matter, because you have to make all the three elements equal. So this, you have to keep this as the unique meeting point. If z merges over here, you still have to keep this as the meeting point, but then if z merges over here in this chain, then you have to keep these as your new meeting point. So you can see that every time you keep on adding elements, your meeting points decreases, but no matter what, your meeting point remains the same, because you can join the chain at only one node. You cannot join it at multiple node, because you have a fixed journey, because once you have joined the chain, you cannot leave the chain. So this means that you only have to deal with one candidate and one candidate only, not 60 candidates. But there is just one exception, which if you were observant enough, that you would have already noticed. And the exception is that when you are doing this, right, we said that we have to stop the process at 1, right? So that's why we said that the process stops at 1, but you know that from 1 you can actually go to 2, but you're not going to 2 to avoid infinite loops. So this means that if you look at our code to figure out, so if you look at this code that goes to the next element, you can see that if 1 is the absorbing state, right? Then if you have something like this, 1 1 1 2 2 2 2 etc., then even in this case you would say that your unique meeting point is 2, because since these are 1, since these are odd, you increment it to 2, because first you do the increment operation and then you do the division operation. So they will be incremented to 2 and their meeting points become 2. But actually when we said that two elements have unique meeting point, this is true 99% of the time, but there is a very small scenario where this is actually not true. What is that case? And that case is 1 and 2. Because if an element is 1, then it can meet at 2, but if an element is 2, it can also meet at 1. So because if you are coming from X, you can either join the chain at X at 1, but you can also join the chain at 2, because you have to come from 2 and then you have to go to 1, but then from 1 you can also go to 2. So this 1 to 2 is a slight exception, but if you can handle it, that is if you see that if your meeting point is either 1, you also consider 2 as your meeting point and vice versa, then you would have handled all the other cases, right? So the only thing that we have to worry about is that we have to take 1 as a candidate, 2 as a candidate, and whatever the unique meeting point that you are getting as a candidate. So we get a maximum of 3 candidates only, not 60 candidates. And with this we can solve the problem in n log n. So first we write the code for computing the unique meeting point. And how do we do that? We say that if you have X and if you have Y, first of all you always try to consider this smaller element and take it to the right hand side as much as possible. That is, if you pick the smaller element and then you go towards the right hand side, so that 1 can meet with 2. If you prefer, you could also deal with the bigger element. In that case you would have to do the division first, but I did from the smaller element perspective. So if you increment X and if you have met Y, then of course that is your meeting point. Otherwise you decrease the bigger element, that's why you go next of Y. And this way you can find out that you don't actually have to iterate over the log n candidates. There are only 2 or a maximum of 3 candidates. Actually, if you think about it, there are 2, but I won't dive deep into the details of why there are 2 candidates and not 3, but doesn't hurt to check 3, right? Like previously you were checking 60, and if you don't want to go through all the implementation detail, you can just see that okay, if your meeting point is 1, also consider 2 as your meeting point, but if your meeting point is 2, also consider it as 1. So in that manner your meeting point can maximum be at 2 location. So you don't worry about minima. You don't actually have to worry about checking if it is reachable or not. Why? Because you're computing the meeting point, and meeting point is of course reachable. And the final code looks something like this. So the final code is very simple. This version, in fact the n log n version is actually simpler to implement. So you compute this meeting point, and of course this takes log n, because in log n steps someone will have to meet at 1, and then you don't actually sort the array and compute the minima. You take the first element and then you compute the common meeting point, and if the meeting point is 1, you consider 2 as well, but if it is 2, you consider 1 as well. So maximum of 2 candidates, and then for each candidates you know that it is always possible to reach it, so you find out the minimum cost to reach it, and then you print the answer. So this final implementation was this final optimization was not necessary, but since this was a problem on ad hoc problem, this was the video on ad hoc problem, I just wanted to add some sharp observations that improves the time complexity of this problem, even though n log square n with simulation also passes this problem. But the main learning I think that you could have from this video is that sometimes you need to focus on the minima, the maxima, and how the sequence of operation change the size of your set. If you are multiplying by 2, then it will, in just log n steps, your set size will explode. If you are dividing by 2, in just log n steps, you will eventually reach a very small number. So these are the learnings that you can apply to future problems as well. Thank you.